Hello, guys. Welcome back to MedZone African Motives. Still working on engineering science and for that is dynamics from the question paper of April 2023. So we are going to be working actually on question number 4. So we are given the first part of our question 4.1, that is a casting with a mass of 45 kgs is placed on an incline with an angle of 25 degrees and the casting is at rest. Take note, it is at rest. The coefficient of friction is 0.4. So now there's a movement that is taking place. That is now where we are given the coefficient of friction where there is a movement. So if we are to take this into consideration, this is on an incline. So let us just have our little diagram here so that we can see how to attempt this question. So that is 4.1. So this is going up like we are having an incline in this case like this at a certain angle of 25 degrees. So this is what we are given to the horizontal. This is going to be at an angle of 25 degrees, the one that you're given. That's 25 degrees here. So what is happening is that we are given a casting here that is at this point. So we have got an object that is at the top, all right? So it's at the top like this. So this is where we are given our object, which is having a mass of 45 kg. So we're given a mass in this case of 45 kgs. So this is having 45 kgs. All right. Having a coefficient of friction before it is at rest. So meaning to say we are going to experience a movement later on from where the object is going downwards like this. So we're going to have a movement. So definitely we are going to have an opposition force that is going to be affecting this object as it is moving. All right. So that's why we are given the coefficient of friction of 0.4. All right. Having our coefficient of friction of 0.4, let us check what we are given here. Calculate the first part of our question was to calculate the frictional force needed to keep the casting at rest. For it to be maintained at rest, what is the frictional force? That is our question in this case. What is going to be the frictional force? All right, so let us take this into consideration. From the coefficient of friction that you are given, we understand that the coefficient of friction is simply equivalent to the frictional force divided to the normal reaction in this case, where we can use this as the perpendicular force, the perpendicular component in this case, which is the perpendicular force to the given force that we are given here. So we are going to have this as our perpendicular force going down here like this, perpendicular to the plane. So this is our F perpendicular like this, or you can write this as FC, which is equivalent to W cos theta, that is the weight times the cosine of theta. By the weight here, we understand this is mass times the gravitational acceleration. So that means we can use this in this case to calculate our coefficient of friction. In place of the normal reaction, we are opposed by what? The perpendicular component in terms of force. So this is going to be the coefficient of friction. So take note, we want to make the coefficient of friction the subject, or you can just substitute on your formula, or just make this the subject of the formula in this case, meaning to say this is like over 1. So you're going to multiply 1 times the coefficient of friction. Thus, we are going to have the coefficient of friction is equal to the frictional force, the coefficient of friction times the perpendicular force in this case. All right. So this is what you're going to have, or FC, whereby or this pi can be substituted with W cos theta or mg cos theta. So that means we are going to have this as the coefficient of friction times mg cosine of theta. That is the mass times the gravitational acceleration in this case. All right. So that's it, guys. We can have our coefficient of friction in this case. Having our, we can have our frictional force because we've got the coefficient of friction of 0.4. So the coefficient there of 0.4 times the mass in this case of 45 kgs. So we're going to have 45 times the gravitational acceleration of 9.8 times the cosine of theta. Our theta is the angle that we are having between, that is the cosine of 25 degrees. All right. So that is, we can have our frictional force from this. So our frictional force, if we are to use our calculators properly, we are going to obtain 159. So that is 159,8726 and so on. So this is going to be 873. All right. So this is the force being measured in newtons in this case. So this force is measured in newtons. So that is a mixture of the units of measurement. All right. So that is actual 2 marks for that. So you just need your formulas, know your formulas and how to substitute into your formulas. All right. 4.12, calculate the force needed to move the casting up the incline. All right. So what is going to be the force for this object or the casting that we have for it to be moved up the incline in this case? All right. So you're talking about F up in this case. So that is going to be the sum of the frictional force. Remember, we are saying here, we have got our parallel component, this force here, we've got our parallel component, all right? So as this object is going up, all right, this object as it is going up, it is being affected by the parallel component to the plane, also affected with the frictional force because there is going to be the frictional force opposing in this direction because we are going up. So it is going to be opposed down. So meaning to say, this F up is simply a combination of these two forces. Remember, we can say the sum of forces that we have to the right is simply equivalent to the sum of forces that we are having to the left in this case. So adding up everything that is to the right, everything that is to the left must be equal, or simply the sum of forces at the point should give us a 0 like that. All right, so this can give us now a combination that we can conclude in this case. All right, so you can have a conclusion that our F up in this case, so that is our F up, which is going to be the sum of these two forces that we are given, which are opposing in the other direction. So you add them together. So we are going to add the frictional force. We obtained this one, and we also need the parallel component in this case. All right, so how are we going to obtain our parallel component? This is taken from W sine theta. So our parallel component is simply W sine theta in this case, which is simply the weight with that is a mg sine theta from the mass that you're given here. So that means we can combine everything at once. In this case, we've got these values. So that means at the end, our F up is going to be the frictional force. We've got our frictional force here. That is 159,873 plus the parallel component. In this case, we say this is mg sine of theta. So that means we're going to multiply 45 times the gravitational acceleration. All right, so this is going to be, since I say this can be given as mg sine of theta. So our mass in this case being 45 times the gravitational acceleration of 9,8 times the sine of theta, the angle theta. Remember, our theta is at 25 degrees. So this is 25 degrees in this case. All right. So this is going to give us our F up. That means all you need is to combine properly on your calculator. All right. So our F up is going to be given as 346. So we're going to have 346,2476 like that, which is going to be 248 to 3 decimal places. All right, measured again in newtons in this case. All right, so make sure when answering this question, understand the information that you're given. Use also what you have on your diagram. Your diagram must also help you to answer these typical questions also with the help of the formula sheet that you'll be given. So on the other part, on question 4.13, we are now asked to calculate the tractive resistance if the casting is moving up, meaning to say the tractive resistance when the casting is moving up the plane, which means we are talking about the F up being included in this case. All right. So how can we have this into consideration? All right. So it follows that since we are talking about, remember we're saying it's F up that we are going to be working with because it's moving up. It's not moving down. It's moving up. So it follows that F up also can be given as, remember we said F up can be given from this formula. The same F up that we are given can be given as F up is equivalent to the tractive force that is the resistance in this case. So this is our tractive resistance times the parallel component in this case. So when you are using the tractive resistance, you multiply to the parallel component, which is the parallel force. All right. So meaning to say, this is what you're supposed to be calculating. So you can simply make this the subject. So you can divide by them. Parallel component here. So meaning to say our TR is going to be F up everything over the parallel component in this case, which is F parallel. So we have got this from our information. Remember, this is our parallel part, which is given from mg sine theta, which we have got this value here. Our F up is, we have got this F up here. So we simply need to substitute into the formula. So that's our TR is going to be F up. We've got 346,248, everything divided to them. F up, which is F parallel, which is given as mg sine of theta, which is this part that we have. So this is 45 times 9,8 times the sine of 25 degrees. So this is just a repetition here, of which you, if you calculated this value before, then what you need is to simply substitute that value. There's no need for you to rewrite all the values. All right, so here we are going to obtain 1,8 5780 and so forth. So this is going to be 858 to 3 decimal places. This is the force. That's a resistance in terms of that's like force. So meaning to say our answer is supposed to be in newtons in this case. So this is how we could have calculated our tractive resistance in this case. All right, so let us check our part, the other part of the question that you're given, which is now on question 4.2. So 4.2, we've got another information that we need to take into consideration of an incline again. All right, so this is also an incline that you are working with. A steel ball with a mass of 12 kgs is at rest on the top of the incline. All right, so we've got something of this nature where it is at the top of the incline. So definitely there's going to be an angle that is going to affect, but we are having this at the top. So this is a steel ball that you are having at the top there. Having a mass of 12 kilograms. So given the mass in this case of 12 kilograms. So this is our mass of 12 kilograms. It is at the top of the incline. The ball starts to roll down the incline. So this time the ball is rolling down the incline. So we are going to be talking about F down instead of F up, meaning to say it is being opposed in the other direction. All right. So the incline, when it is rolling down, it is rolling on an incline of 30 meters. All right. So meaning to say from this point where it is up to the ground, down to the ground, in this case, we have got a distance that we are given. This is linear from our linear information. So this is just our S. So our S is given as 30 meters or distance, whatever way that you can write. All right. With a slope of 1 in 25. So take note of what you're given here. We are given a slope of 1 in 25, which is a gradient of 1 in 25. That is 1 over 25. So that means from our gradient, we can use the tan of theta. From our tan of theta, we can calculate the angle theta that is affecting here. What is the angle that is affecting? So we know that the tan of theta is equivalent to 1 over 25. So to find the theta, it is going to be arctan 1 over 25 in this case, arctan 1 over 25. So that's our theta is going to be something like 2 point. So that's 2.2 291 degrees. All right. But remember what I said previous that on a condition that you are working with tan, this is tan of theta, which is 1 over 25. 1 over 25, we are talking about a decimal of 0.00 something, which is a small value that we are talking about there. So whenever you are referring to small values, it follows that the tan of theta is going to be approximating to the sine of theta. Whenever theta is small, we're talking about small angles in this case. So the tan of theta is going to approximate to the sine of theta. Check all your theta 2,2, say 2,2. It's a very, very small angle that we're talking about there. But you can actually use these values as they are, which is still one and the same thing. You can use the values, the angle in degrees as it is, it's still one and the same thing. So what I'm simply trying to say is that the values that you're going to be having are simply going to be approximately equivalent or approximately the same, not having exact values, but approximately. That is what we are saying there. All right. So meaning to say, all right, so this is, let us check our questions here. Like I said, for this information, in place of tan, you can even use the sign, which is fine. So our question was ignoring friction. All right, so this part of friction that I was indicating here, they are saying we must not include this one, ignore this part. Calculate 4.21, the loss in potential energy if it rolled 15 meters. Remember, the ball is going to the ground, which is 30 meters to the ground. But now they're saying this ball just rolled for 15 meters, which means it's at the half of what? Of the point. It just rolled 15 meters. We are remaining with another 15 meters on this part. So if it rolled for these 15 meters, what is the loss in potential energy? That is our question there. So take note of our information. For the 15 meters, but before it was 30 meters, the distance that you're given. All right. So knowing that our potential energy can be calculated, remember, that's 4.21 here. We can say our potential energy from mgh, we have got mgh in this case. But this height now that we are referring to is this one. Take note of the height that you're supposed to take. We are supposed to take this height at a certain point, but not at 30 meters, but at 15 meters. And this h being affected by the angle of theta in this case, we are going to find that this h can be given as s sine of theta, which is the displacement, our s here, sine of theta. Or you can just write, if you are saying this is h, then you can write h sine theta, but this is simply s sine theta in this case. So meaning to say, on our formula here, we are going to have this as mgh times s sine of theta. Some, they can just use h, but this s is simply this displacement that you're given, the distance that you're given. But for the 15 meters that we have, so meaning to say, we are going to have our mass of 12 kgs times the gravitational acceleration of 9,8 times the distance, that is our s in this case here, not 30 meters, but for the 15 meters that it is rolled. So it rolled for 15 meters times the sine of theta. So the sine of theta now, that is the angle that we are having here, which is 2,291 degrees. All right. So this is going to give us 70,503 like that. So you're going to obtain 70,5036 and so on. So this is going to be 504,504 to 3 decimal places. You're going to have 4 in joules in this case. But if we are to consider this way, that at a condition that theta is small, then tan of theta is approximating to the sine of theta. It means that we were going to have our formula as the same part that we gave, that is going to be mg times s sine of theta. So meaning to say, we are going to have the mass as it is, the 12 that we had before, that was 12 times 9,8 times the distance, which is the distance of 15 meters. Remember, it rolled for 15 meters. So we are going to have this. I want you to be careful about this part. We are going to have this 15 meters times sine of theta, which we are saying is being an approximation of tan theta. So if it is an approximation of tan theta, what is going to happen? Let us see what is going to happen here. We are simply saying we are approximating that we are going to use the value of tan theta, and we have that value of tan theta, which is 1/25. So meaning to say here, we can use the value of 1/25 instead of using sine of this angle. So meaning to say here, we are going to obtain something like 70,5 joules. So this one is giving us exact value 70,5. So if you take these values, they're actually the same. 70,5 on this one, we obtained 70,504 when we used sine 2,21 and so forth, of which if you are to use this as the exact value, you're going to see that this will be one and the same thing. One and the same thing, actually. So this is 0.56, all right? So there is 0.56 here, or if you use this one, it is going to be 0.56 here. So take note, but actually approximating to one and the same thing. So that is how we can attempt these typical questions. Then if you check on 4.22, you're given the speed of the ball if it rolled 30 meters. Now they are referring to the whole ground now, to the whole distance of 30 meters. We are including the whole distance of what? 30 meters. What is going to be the speed? All right. So how can we calculate the speed? Let us see what we are having on our information. Let us see. We are having the potential energy. All right. We are having the distance, which is 30 meters. Let's just take this into consideration and see. So that is question 4.22. We have got question 4.22 in this case. We are supposed to calculate the velocity. We do not know this value. We are given the distance, 30 meters, our S being 30 meters in this case. That is what we have for the meantime. All right. If we are to consider the velocity, take note, there's this part that we understand for the energy between the potential and the kinetic, that we remember there is the energy cannot be lost, but it can be converted from one form to another. So meaning to say there's a condition where we are going to see that our potential energy and the kinetic energy, they'll be the same. We are going to have a condition where by the kinetic energy will be equal to the potential energy. On this condition, we know that our kinetic energy is calculated from half mv squared, half times mass times velocity squared, which is equivalent to the potential energy, which we know is calculated as mgh, whereby we need now to have the height in this case. We are supposed to work with the height. All right. Having this into consideration that we are supposed to work with the height, okay? Let us make V the suppose we want to calculate V. We can divide the mass because this is the same, so these two can cancel. So what can we do? To transpose this, we can multiply both sides by 2. Since this is a half, so you can simply multiply by 2 or just cross multiply. So meaning to say, we are going to end with V squared, thus this can cancel, V squared being equal to 2GH. So that's 2GH like this. Making V the subject, that means we are going to introduce the square root. The square root both sides of V is going to be equivalent to the square root of 2GH. Having this in mind, we can be able to calculate this velocity that we need here, because we are saying our velocity can be calculated from the square root of 2GH, which is supposed to be also known. This formula, you're also supposed to know this formula. Yes, you can rewrite from, you can formulate the formula for V from this way that I did here, but you're supposed to also know this formula. So it can be an advantage if you know it, but if you do not know, therefore try to manipulate V to be the subject of formula from this too, because kinetic energy is equal to the potential energy since energy is not lost. but can be converted from one form to another. So we have the gravitational acceleration, but what about h? Our h in this case is taken from the distance because we are saying it's 30 meters. Just like this part where we said h is equal to s sine theta. So meaning to say we are supposed to calculate h now when our distance, our s is at what? 50 meters, because there we are having our s as 30 meters. So meaning to say our formula is going to be given as v is equal to the square root of 2 times the gravitational acceleration times our h now, which is s sine theta. So this is going to be s sine theta, just like the previous part, whereby our s now is at 30 meters. So we can find our value. That's substitute here. We're going to have the square root of, so this is going to give us the square root of 2 times the gravitational acceleration of 9,8, the distance of movement, the distance moved being 30 meters at that condition, times the sine of theta. So just like the previous part that we had, we can have our sine of theta from the angle that we have, because already we've got our angle here, 2,291. So we can use our angle 2,291. So this is going to be 2,291. That's sine here. Sorry, this is sine theta. So this is going to be sine 2,291 degrees. So we can actually use that angle. If you are to use the angle, which is fine, we are going to obtain our velocity in this case, which is going to be something like 4,848 in meters per second. If we were to use a consideration that we used previous, that the sine of theta approximate to the tan of theta, where we said the sine of theta can also be written the same way with 1/25. We are going to see that our height in this case is going to be like this. Our height is going to be taken as h, remember, is equivalent to s sine theta, whereby our s is the displacement of 30 meters. So it's 30 times the sine of theta. We are saying it's an approximation to tan, which is 1/25, just like the previous case that we had. So if this is going to give us 1/25, therefore you are going to obtain your h as 1,2 meters. Therefore, our v from our formula here, we are going to see that our v is going to be the square root of 2 times the gravitational acceleration of 9,8 times the height, which is h. So our height is 1,2 from this approximation that sine approximates to tan of theta. That's, we are going to obtain our v as 4,85 in meters per second. So as you can see, it's just one and the same thing, 4,85. This one is giving us 4,848, which is just one and the same thing, and the same approximation that we are having. So this is how we can answer these typical questions. What we need is to work on more question papers as we are revising for the exams which are ahead of time. But for now, that's it, guys, for Maison African Motives, working on engineering science, and for till we meet again.